Bonding. So right now we're going to start out with a little bit on, I like to call this more on ionic compounds. More on ionic compounds. So this little chart we're going to be drawing is how a molecule forms. So how does a molecule form? We got a new type of Christmas tree this year, and it literally scratched my arm. Like, do you guys see that?
Mine did that too.
I got destroyed. Yeah,
like,
I don't know if it's breaking out or like a scratch.
It was like white scratches all down my arm.
Yeah, anyways, how a molecule forms. Sorry. So this is called, and this isn't super important, but you guys should know this, is the Born-Haber process. The Born-Haber process. This is essentially like Hess's law, okay? You guys remember Hess's law where you're flipping things to make them equal, and then like if you divide by 2, you divide by 2. If you flip it, you flip the sign. Yes? Yeah. This is essentially that, just in a different form, okay? So basically you're just going to add everything up and subtract. But I'm going to show you the process first, which is actually more difficult than we have to actually do. Cool? Okay. So you're going to want to skip, I don't know, how many lines that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Go down the 11th line. And we're going to make a little thing over here. And this is going to be our energy line. So this is going to be our energy in kilojoules. Here's our energy in kilojoules. It's going to be increasing as I'm moving up this scale. So skip the first, 1, 2, 3 lines. All right. And let's start here. So we are going to create lithium fluoride. So I'm going to show you the process, how this actually happens. Because when you create lithium fluoride, what you see is, boom, lithium fluoride. So I'm going to talk you through the process of how this breaks down into steps. So here is my solid lithium. Lithium as a solid. Can you guys see that okay?
Yeah.
Should I zoom in a little bit more? So I have lithium as a solid, plus, when I'm actually adding this, this is actually plus 1/2 mole of F2 gas. So lithium solid plus 1/2 of F2 gas. So it's very difficult to react a gas with a solid. Agreed?
Yeah.
Yes? What would it be more easier to react a gas with? A gas. A gas with a gas. So I am going to sublimate my lithium. So now I'm going to have lithium gas, now I have lithium gas, plus still 1/2 of a mole of fluorine gas. And this energy it took to do this sublimation is called sublimation energy. Why is that? Because sublimation. All right, sublimation is 161 kilojoules. So it took 161 kilojoules of energy to sublime the lithium into a gas. Are you with me so far?
Yes.
All right, just stay with me. All right, now, so I have lithium gas plus fluorine gas. The next thing I have to do is I have to, can I really react a gas with a gas? What actually reacts in chemistry? What?
Molecules.
Ions. So now I need to ionize this lithium. So now I'm going to have my lithium ion, which is positive gas, plus 1/2 still F2 gas. Guess what this energy is called? Ionization energy. So I ripped off an electron. So my ionization energy is 520 kilojoules. So at this point, I have lithium ion, and I have 1/2 mole of fluorine gas. And I'm going to go up one more time. And now I'm ending up with lithium ion, which is a gas, plus fluorine gas. So what have I done here to get fluorine and not just 1/2 F2?
You split F2 into F.
So what I actually did was I formed a bond, is what I did. So to go from F2 to just F, I basically formed a bond. Stay with me. I formed a bond, just trust me, okay? And this was 77 kilojoules. 77 kilojoules. I know, super interesting. Now, I have lithium ion plus fluorine gas. Am I going to be able to react those two?
No, you need iron.
I need ions, yes. So I'm going to go down a little bit. And now I'm going to have lithium ion, which is a gas, plus fluorine ion, which is a gas. Fluorine is obviously negative. Fluorine is negative. So what did I have to do to fluorine? Well, what does fluorine want to do with an electron? It wants to gain. So guess what this energy is called? Not ionization energy, but this is going to be my, when you want to gain an electron, what's that called? The electron affinity energy, yes. The electron affinity energy, which is now, I'm going down, so this is negative 328 kilojoules. And now I'm ready to actually make this into something stable. So I'm going to go all the way down here, back to the bottom. And I finally have lithium fluoride, which is a solid. But I have one more energy here. All right? When I form the lithium fluoride, what are ionic compounds? What structure are they in? Lattice. This is the lattice energy. All right? This is the lattice energy. So this is negative 1,047 kilojoules. So that's my lattice energy. Because we know that it's super stable, so it's going to be giving off energy. If I wanted to figure out delta H of the reaction, all I would do is, well, this is it, right? So right here, in between here is going to be my delta H of the reaction. And the way I'm going to figure that out is delta H of the reaction is sublimation energy plus ionization energy plus bond energy plus electron affinity plus lattice energy. So what I just showed you is basically you add them up. All you have to do is add them up. I was going to kind of show you the whole process. Someone was discussing this on my Facebook group the other day for AP Chem. Yeah, there's an AP Chemistry Facebook group. Imagine that. All right.
You gotta sign up for Facebook now.
It's all teachers. It's all teachers. It's like memes and just funny stuff posted there. And like anytime they post like, what's this piece of lab equipment? And someone will be like, a bong. Like everything there was like, it's a bong. Like because it's just, yeah. Anyways, all you guys really have to know is you just add them all up. Okay? And occasionally, like let's say it's like 2 Li. If you're working on this, well, you'd have to multiply this number by 2. So the Born-Haber process is basically Hess's law, but you're just adding them all up. So if I add all of these numbers up, my delta H reaction ends up being negative 617 kilojoules. So when you're working through a problem like this, you might have to divide your ionization energy by 2, or you might have to multiply your electron affinity by 2. That's all this is. Yes?
Wait, when did you say you divided and multiplied?
So let's say it was, they gave you a problem, they give you the ionization energy, right? Well, this is the ionization energy of like 1 Li, but it might be 2 Li in the book. So you just have to figure out what you're multiplying or dividing by down here. That's it. So they're like, you don't even really need to know the Born-Haber process, but you just need to know adding them up. So basically you add them up, you write a sum, and that's it. Are you guys okay with that? Sure. Okay. What's actually going on? It's not super important, but it's kind of cool. Lattice energy. Lattice energy. Let's define that. Let's actually define that. This is the energy required. To separate. I cannot write today, guys. I literally cannot write or talk. The energy required to separate a mole of an ionic solid into gaseous ions. That's actually the technical definition of lattice energy. The energy required to separate a mole of an ionic solid into gaseous ions. So, if I asked you which set has the higher lattice energy, all right, which one would have a higher lattice energy? Calcium fluoride or magnesium fluoride? So, which has the higher lattice energy, calcium fluoride or magnesium fluoride? Which one will take more energy to separate into gaseous ions. Which one is going to take more energy to separate into gaseous ions? Guess what this is based off of? Coulomb's law, right?
Oh, right.
It's just Coulomb's law, right?
Pretty cool.
Fluorine's the same in both, yes?
Yes.
Okay, so it's going to be harder to separate it if something is closer together, yes? So it's magnesium fluoride, right?
Wait, why?
Magnesium is smaller, right?
Right?
Magnesium is smaller and more tightly bound to the fluorine than the calcium is.
I wanted to say it, but I didn't.
So magnesium is smaller, yes? Whichever one is smaller is going to be harder to break apart, is what it comes down to.
Okay.
Because this is the energy required to separate a mole of ionic solid into its ions, whichever one's closer is going to be harder to break apart. That's it. That's Coulomb's law.
Further apart, one more shell.
Yeah, calcium has more shielding. You got it. Shielding. Okay. I think I can fit this. Now I'm going to turn the page. I write too big. Okay, next part's also super easy. This is bond energies. Open up your book to page 323. Page 323 in your book. Open up your book. So I'm going to give you an equation. CH4 plus 2O2 yields. This is combustion. CO2 plus 2H2O. So here's the equation. If you don't have a book, get with a partner that has a book. Get with a partner that has a book. So, my goal is to figure out, go for it. If you need to move, you need to move. I could ask you, what is delta H reaction of this based off of the bond energies? So, the first thing I would suggest doing is drawing out these molecules. So today is when we're going to start drawing molecules and start drawing Lewis structures. So CH4, pretty easy to draw, right? This is going to be carbon connected to a hydrogen, connected to a hydrogen, connected to a hydrogen, connected to a hydrogen. Are you guys good with that?
Easy.
We've already drawn oxygen. Oxygen is double bonded to another oxygen with 2 lone pairs. Agreed? Yes? We've done that, right? I think we have. Have we done carbon dioxide? I think we did a while ago. Carbon is double bonded to 2 oxygens, both with 2 lone pairs. I think when we talked about sharing electrons, covalent compounds, we might have. And then water is H connected to O connected to H, right? And water has lone pairs. Well, they're actually both at the top. That's fine. Just draw like this for now. We'll fix it tomorrow. And I have 2 of these, and I have 2 of these. So this is what I like to do. I like to draw out the bonds first. The equation for bond energies is delta H reaction. Delta H reaction is equal to the sum, so this is very similar to what we've been doing, of the bond energies of the broken bonds minus the sum of the bond energies of the formed. This is a little bit different than what we've been doing, because everything up to this point has been products minus reactants. This is technically the opposite, right? Would you agree that this is technically the opposite? Where am I breaking the bonds? I'm going to break the bonds in the reactants, agreed? And I'm going to be forming bonds in the products. So this is actually the opposite of what we've been doing. So bonds broken minus bonds formed. So here we go. Let's just work through this. So delta H of the reaction is equal to, so let's do carbon-hydrogen bonds. How many moles of carbon-hydrogen bonds do I have? 4. Do you guys agree? 1, 2, 3, 4 carbon-hydrogen bonds. So you guys okay with that? Okay. So I have 4 moles of CH bonds. Just 4. I'm counting. 1, 2, 3, 4.
our stir bars.
Have you seen them?
There's like one in there.
Really?
Yeah.
In the prep room, or
No, in the, in like where the students vote. Yeah.
did you check with the magnetic ones or with the hot pads?
I checked in both spots.
Really?
Yeah.
I don't know.
I don't know if somebody uses them or not. Okay. Maybe we should order more of those too.
There might be some in one of the little skinny set of drawers in the
Yeah,
prep
check
room.
there.
They're not there?
Yeah.
Oh.
That's the only one I found.
We just ordered more, so I don't know.
Yeah. Yeah, we'll just have extra.
Okay.
Well,
I want to read that book about the mystery of philosophy.
Yes. Sean, I'm just counting. There's 1, 2, 3, 4 carbon hydrogen single bonds.
Okay.
On page 323, how much energy is there in a carbon hydrogen single bond?
413 kilojoules per mole.
Yep, so this is going to be times 413 kilojoules per mole. I'm multiplying those together. Plus
Where did that number come from?
That's from
this number from the book. So does everybody understand where that number came from? Carbon hydrogen bond, page 413.
Yes.
Plus, how many oxygen double bonded to oxygen bonds do I have?
2.
2.
Yeah, I've got 2 moles of O double bonded to O. Times, what is the energy for an oxygen double bonded to an energy? I'm sorry, oxygen double bonded to an oxygen. 495. 495 kilojoules. Would you agree that that is all the bonds broken?
Yeah.
Yes? Minus. Bonds formed. So what new bonds do I have on the other side? Did I have any carbon double bonded to oxygen on this side?
I think not.
No. So how many do I have formed on this side?
2.
2. So I have minus 2 moles of carbon double bonded to oxygen times, what is the energy for carbon double bonded to oxygen?
799.
Oh, wait a second.
Asterisk.
There's an asterisk.
It's like a star.
Follow below. Carbon double bonded to oxygen, do you see the asterisks?
Yeah.
It's only one.
So it's CO2, it's different.
Is this CO2?
Sure is.
Yeah.
It sure is. So what's the actual energy?
That's 799.
799. Good job following the asterisks.
Oh, these go down.
Yes. When there's an asterisk, you go to the bottom of the thing. Yes. Plus, how many hydrogen oxygen single bonds have been formed?
That's 2.
No. That's 4. Because there's 1, 2 times 2, which is 4. So plus 4 H to O's, 4 moles of those, times what is the hydrogen oxygen single bond?
467.
You guys okay with that? 467? Yes.
Why did we not do 2 for the O2?
I did. There's 2 double bonds. 2,
Oh,
Double
double
bonds.
bonds. Okay.
right. 2 actual double bonds. Good question. 4 H2O times 467 kilojoules per mole. Get out your calculator and do it. Not hard, just a little bit of work. What is your delta H reaction? Somebody pull the door, please. What'd you get, Sean?
I'm fixing my hair.
Oh, got it. Trey, did you get it?
Negative 824.
That's what I got. I got negative 824. This is just going to be, well, that's going to be kilojoules. Or wait. Yeah, kilojoules. Wait a second.
I just messed. Wait, how'd you get negative?
It's just kilojoules.
It's just
right?
yeah, just
kilojoules
kilojoules,
counts,
right?
I'm wrong.
Per mole of CH4.
Let me make sure. Yeah, just kilojoules. That makes sense. Negative 824 kilojoules. So I could put that up here, right, into my original equation as delta H equals negative 824 kilojoules, just like we've been doing. So that's bond energy. Super easy. You just have to you'll have to be given, I can't talk today, the bond energies in some kind of chart in order to do that. Okay. Put a squiggly there. Because we're going to something completely different now. Okay. So this is the introduction to bonding structures. Now I'm going to blow your mind. Okay? So we're going to start out with CH4 because we were just talking about that. So the first thing that I want to do is draw out the off-ball diagram for the outermost electrons on carbon. So carbon. What would be the outermost electrons for carbon? What orbitals? 2s. Okay, I like that. So here are my 2s electrons, and how many are there in there?
That's 2.
One up, one down. Agreed? You guys okay with me here with me so far? And then how many 2p do I have?
2 up.
I've got one up, one up. Are you guys okay with me so far? Yes? So, how many hydrogens want to bond to carbon? 4. How many spots do I have to actually bond a hydrogen though?
No, less than.
How many?
5,
No.
3, 4.
No.
4.
How many spots do I have to bond an actual electron? I only have 2 spots, agreed? Because in order to bond, I have to have a lone electron. Are you guys ready for this? I am going to promote this electron.
What?
All right? This electron is going to be promoted. All right? Up to here. Okay? I promoted that electron.
You're promoting the down arrow or the up arrow?
Well, once I move it here, it becomes an up arrow. Right? Once I take this electron away, it's turning into an up arrow here. I now have a hybridized orbital. All right? Because now this isn't here. Agreed? This is gone. How many spots do I have to bond a hydrogen now? 1, 2, 3, 4 spots. Yes? So, do you guys see that I have 4 spots now? The s orbital looks like what? What does the s orbital look like? We talked about this.
So it's a sphere.
A sphere. So the p orbital looks like a dumbbell. Okay? But what we've created here is not an s or a p. We've created a sp. An sp hybridized orbital. So an sp orbital kind of looks like this. All right? It kind of looks like this. All right? That's kind of what an sp hybridized orbital looks like. All right? So kind of like this. The drawing's not super important, okay? The drawing's not super important. I'm showing you the long part of this. There's a shortcut to all of this, okay? But you guys have to kind of understand this part. So, if I was going to draw this, how many sp hybridized orbitals do I have here? There's 4, right? Yes? So if I was going to draw this, I would have like one like this. There's one. I would have one like this. There's 2. I would have one coming out like this. There's 3. And I'd have one kind of coming this way. All right? You have to kind of imagine in your head, kind of coming out at you.
Oh, it's like 40.
It's kind of like, well, it's 3D,
3D.
right? But I've got 4 sp orbitals here. So, can anybody envision what this molecule would look like? If I had a hydrogen, a hydrogen, a hydrogen. So there'd be a hydrogen, right? What'd you say? Yeah, that'd be a tetrahedral, right? Because what I would have, all right, what I would have would be a trigonal base. All right? Stay with me.
These words are too big.
I know. We're getting into real chemistry, guys. So if I looked at it like this, right? I have a triangle, a base. Do you see the triangle here? And then there's one coming up. Yes? Do you guys kind of see how there's a triangle and then like one coming up a little bit? Yes? So this as a trigonal base plus one rising, plus 1 rising. So this is considered tetrahedral. This is a tetrahedral molecule. All right? And this is, I would call this officially sp3 hybridized.
Why is it three?
sp3 hybridized because I have one of my s orbitals that got hybridized. And how many of my p orbitals got hybridized? How many of p orbitals are hybridized? 3, right? So I have 1 s and 3 p's. That's where my electrons are going.
What does that say there?
So this says sp3 hybridized. Stay with me, okay? Welcome to real chemistry. This actually isn't that bad. All right?
Take me back.
All right, I know. Take you back.
Take me back to the
So this is where we're going.
red pill, please.
Yeah.
Red pill.
This is where we're going. So I have 1 s orbital. This is basically saying I have a hydrogen connecting to 1 of my s and 3 of my p's. This is sp3 hybridized. 4 bonding sites. Are we good so far? Kind of.
What does that say? Trigonal base.
Trigonal base plus 1 rising.
That's what
This
I
is
wrote.
tetrahedral.
You have
So
five?
I'm working you into tomorrow slow. All right? Who is like, I do not envision this well in my head at all.
My
I
brain
mean, I know what
isn't-
it looks like.
My
I
brain
know-
You did it in your head. You knew it. You envisioned it.
Well, I just don't know what an
Who
SP
kind of-
hybridized is. Or
Okay, we'll get to that more. Okay, we'll get to that more. I'm talking about this shape here.
Okay.
We're doing balloons tomorrow.
Oh.
Yes.
It's like,
We're doing balloons tomorrow.
I just know it looks like.
Yes.
It would look like a stand.
It's a tripod.
It would be like
legs.
3 legs and 1 coming up. Yeah.
Oh,
Like a
okay,
pyramid?
Like a tetrahedral. That's what a pyramid kind of looks like. Except for, wait, no, that's different.
It's like
Not a pyramid, actually.
Pyramids.
Yeah.
It'd be a trigonal
It's
pyramid.
like a-
Pyramids have 4 on the bottom.
It's like a tripod?
It's like a tripod. Yes. Yes.
So is it just like?
Dude.
Is it just like
Make
4
an
sticks?
electron in the s
4
orbital.
sticks coming out of like a dot.
Make it s
Kind of like a triangle.
independent of hydrogen electron to change how
Okay. Shh, 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 shh. Allison, that's a good question. Shh, shh. Ask the question again.
Why would promoting the electron from the s orbital change how it looks in relation to the carbon? Wouldn't it change in relation to the hydrogen, like what bonds with it changes its shape?
So this is based off of whatever's in the middle, what it's bonding to. So the hydrogen is bonding to the carbon. I mean, technically it's both, right? But it's all based off of the thing that's the most electronegative is what it comes down to in the middle. So this is all about the thing in the middle, which you'll see more as we get to this tomorrow. This is just a very, very basic. What you have to know, this is sp3 hybridized. Are we going to even be drawing this? No. There's a way to know this like without even worrying about the drawing. But I'm trying to show you the drawing first. Okay? So, here we go. Let's continue into the murky waters. All right? It's got to get murkier before it gets clearer. So, let's actually talk about Lewis structures. So we've been drawing some Lewis structures, but we haven't actually talked about what you have to actually do to draw a Lewis structure. So there's a couple steps. Step 1, sum your valence electrons. So you're going to add your valence electrons together. Step 2 is use a pair of electrons. Use a pair of electrons, which will be shared. A shared pair of electrons to form bonds. And we did this a little bit on the notes of just a bond is a dash. And then step 3 is satisfy what rule? No, good guess though. The octet rule. Satisfy the octet rule. Or, parentheses, duet. Or the duet rule. Because for some, right,
Oh, there's 2.
they only want 2, right? They only want 2. So, if I was going to say, let's draw a Lewis structure for water. H2O. H2O. So, how many valence electrons does hydrogen have?
1.
1. 1 times how many though?
2.
Okay, so I have 1 times 2 plus how many valence electrons does oxygen have?
2.
No.
6.
6. So I have 1 times 2 plus 6. So my total valence electrons for water is 8. So I have 8 valence electrons for water. So I know that I have to show 8 electrons somehow on my Lewis structure, right? What's going to go in the middle for water? You guys already know this.
The oxygen.
Oxygen, right? So here's my oxygen. I know I'm going to have a hydrogen connected here and a hydrogen connected here. How many electrons have I accounted for so far?
2.
4. Each bond is 2 electrons that are shared, right? Each bond is 2 shared electrons. So I've accounted for 4 electrons. Can I add any more bonds for hydrogen, right? No, hydrogen only wants 2, yes? So this is going to leave 2 lone pairs for oxygen. It's going to leave 2 lone pairs for oxygen. And now I have shown 2, 4, 6, 8 total electrons, and that is the Lewis structure for water.
Does it matter where you put
It looks like a spider.
Yes. So, doesn't matter where I put these electrons. The electrons, all the electrons want to be as far away from other electrons as possible. So because I've got 2 coming down here, if I put these 2 up here, they can repel more. Tomorrow, VESPER stands for valence shell electron pair repulsion theory. So, we want to repel, the electrons want to be as far away from each other as they possibly can, is what I'm saying.
The one that we did on the other one wrong then?
That was wrong, yeah. That's why I said we'll fix it on the next page.
Okay.
Yeah, that was wrong, the water we drew on the other one. But it was, the lone pairs weren't important on that. Now they are. So this would be what it actually looks like. So let's do PBr3. Let's do another one. PBr3. PBr3.
Can you move it?
Oh, sorry. I'll zoom out a little bit. So PBr3. How many valence electrons does potassium have? 5?
Wait.
Phosphorus, sorry. I tell me my brain's not working today.
I was
Phosphorus
5.
is 5. Bromine has 7 times 3 for a total of 26. I've got 26 valence electrons I have to show. Agreed?
Sure.
Okay. So let's satisfy some octet rules. What's going to go in the middle? P.
How do we know this?
Well, the single element's going to go in the middle. Oh, every time. The single element's going to go in the middle.
What if there's 2? Oh, there.
There won't be. So, let's do Br. Let's draw our original out of Br. How many electrons have I accounted for so far? 6. All these bromines should have how many lone pairs around the outside? 3 lone pairs, right? Because they all want to have 8. Agreed?
Yes.
Okay. How many electrons have I shown so far? At this point, it's pretty easy.
24.
Because if you have 3 lone pairs, that's 6 plus 2 is 8, right? 8, 16, 24. Yes? So what am I going to leave on phosphorus?
2.
A lone pair. So that is the Lewis structure for potassium tribromide.
Actually?
Phosphorus tribromide.
Just like them bonding.
What?
Basically just like them bonding and just showing the electrons that haven't bonded.
Basically. Yeah, these are unbonded or lone pair electrons. So there's a bunch of lone pairs.
Why did it put 6?
Because the octet rule, these all want to have 8, a full outer shell, right? The octet rule is they want to have a full outer shell, they want to have 8 around it. So every one of these atoms has 8 electrons, shared or around it. Got it? Phosphorus has 2, 4, 6, 8. Bromine has 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8.
Oh, because the one represents.
Yes.
That's where I could get it.
Now, here's where it gets tricky. Let's do HCN. What is CN on the back of your periodic table? So this is hydrocyanic acid, right? Name isn't important. But how many electrons valence does hydrogen have? 1. Carbon has 4, and nitrogen has 5 for a total of 10 electrons. It's Monday. It's okay. All right? I'm with you. All right? It's Monday. So, what is going to go in the middle here?
This 8. Come on.
It's going to go in the middle. Carbon, right? Carbon's going to go in the middle, right?
In the middle.
Carbon always goes in the middle,
Carbon.
all right?
It's
I
just
heart
a no.
carbon.
What?
That's a no, or just?
Well, carbon is, if you have carbon, carbon is going to be probably the most electronegative out of all of those.
Nitrogen.
Because it's
Let's see, which one's more electronegative, carbon or nitrogen?
Nitrogen.
Oh, sorry, not the most electronegative, all right? Guys, I cannot think today, I'm telling you, all right?
It's okay.
My brain does
We're
not work
with you.
today.
We just
But-
work together.
Carbon's just the best.
If you got carbon, carbon has 4 bonding sites, all right? Carbon's going to go in the middle, all right? Always.
Okay.
And yeah, always. Carbon always goes in the middle. Trey?
I was gonna say, is it because it didn't have 4
Right, because carbon can fulfill the octet rule very easily. And it's got 4 bonding sites. So here we go. I'm going to connect an H here. I'm going to connect an N here.
Why is it like sideways? Can you like up or down?
What? What is sideways?
Horizontal. Horizontal, yeah.
I don't care how you draw it.
Oh.
All right? I just usually draw things left to right. Let's add our lone pairs around nitrogen.
So it would be 4. What? I'm lost again. Oh.
They all want to have 8, agreed?
Agreed.
How many electrons have I shown here?
8.
Total.
10.
I've shown 10 electrons, agreed?
Oh, yes.
Whoa.
Have I satisfied the octet rule for everybody, though?
No.
I have not. Oh, that doesn't work.
Oh,
Wait, this is
one.
That doesn't work. Carbon only has 4 electrons, right? Agreed?
Yeah.
On this picture?
Carbon?
Carbon only has 4. Nitrogen's happy, but carbon's not.
Mm-hmm.
That will not work. Let's try something different. What if I did HCN like this, and I put a lone pair here, a lone pair here? Now does carbon have 8?
yes.
But how many do I have left for nitrogen? I only have 1 lone pair left, yes? Will this model work?
No.
No. Okay. Let's make a double bond. That's a better idea. Carbon double bonded to nitrogen, single bonded to hydrogen, because it can never have a double bond for hydrogen. Agreed? Yes? And I'm going to give 2 lone pairs to nitrogen. Did I show 10 valence electrons? Have I shown 10? 2, 4,
Yeah.
6, 8, 10.
Yes.
Does this work?
No.
No, carbon only has 6 electrons in this one.
What?
Triple one?
Triple bond. Let's see if that works.
I think so.
Hydrogen, carbon, triple bonded to nitrogen. Is everybody happy?
Well, maybe. I mean, for
Everybody is happy. All right? Hydrogen has 2, carbon has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8.
Wow.
So you can just choose the bonds, it's not like, it doesn't matter.
What do you mean choose? I have to fulfill the octet rule. This is the only possible correct Lewis structure.
So the bonds, yeah,
I mean, as you get working on these, you'll just know that's going to have to be a double or a triple bond.
Okay.
I was just showing you all these other wrong ones. All right? Because when you're thinking, oh, I've got 10 electrons, you should be already thinking there's going to be a double or triple bond here. Because it's not going to work. Okay? Okay, are you with me so far?
Sure.
All right, so in chemistry, there's always exceptions.
What? No.
Yes. So here's the exceptions to the octet rule. Here's the exceptions to the octet rule. I think you guys are going to like how I do this. The first exception is boron. Let's do a Lewis dot structure for BH3. Draw the Lewis structure for BH3 right over here. You'll see why. So draw BH3. I know.
Why is there B?
Is that just like, what's the thing next to the B? Just empty space.
Dot, 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 dot. I don't know. I don't know why I did that. You don't even have to draw that.
What's on BH?
This is just what my brain did. My brain is just doing things. Boron has how many valence electrons? 3 times 1 for hydrogen is 3. So I'm going to show a total of. Okay, so I have B, H, H, H.
No, hydrogen has 1.
Hydrogen has 1.
Wait. Yeah.
Would that be correct?
Yeah, that's already 6, right?
That's already 6.
But they don't have 8.
That's an exception to the rule.
Oh.
So boron does not have to have a full 8. It's an exception. There's only 6 valence electrons here, agreed?
Yeah.
Yes? And there's only 6 valence electrons I can only draw with 6 valence electrons, yes?
Yeah.
That's true.
That's an exception.
Something's up. Is aluminum? What's
That's fishy.
Because it's boron only has 3 bonding sites.
Is that stable?
That's stable. That is stable. Now, what about sulfur? Sulfur. Let's do SF4.
You did the dot dot dots again.
I don't know why I'm doing the dot dot dots, okay? SF4. Draw the Lewis structure for that.
Would it be like anything that bonds with boron that rule applies to, or is it just hydrogen?
Well, really it just depends. It just depends what's bonding.
That's a lot of depending.
So draw the Lewis structure for SF4. At least try it.
Right?
2, 4, 6, 8. I don't like that.
What?
I don't think sulfur can
Wait,
do
that's
that.
not possible.
Sulfur cannot do this.
It is possible because this is an exception to the rule. Did you guys get this far?
Sure.
Well, you
Yeah.
went kind of like.
Yeah, definitely.
Yeah, I did that.
I'm a little behind that. But yeah.
Sorry.
Yeah, we're getting.
I just was afraid to do that.
We're missing 2 here.
I'm still.
Would you agree? I still have 2 more electrons I got to put somewhere.
I would agree.
But the
Make
Well,
a double
bond.
bond on one of them.
That wouldn't work.
What if
No,
I just get
this
rid
is-
of
All right, that would just take away a lone pair from here, right?
Make it.
Sulfur has what we call an expanded octet possible.
No! No more.
Throw in
Yeah, I expanded the octet. Look at that. Did you see how I just expanded the octet on sulfur? Wasn't that awesome?
That's just
Boom.
Why?
Because sulfur can have an expanded octet. All right?
It's not enough.
So what it comes down to is these exceptions to the octet rule are BS. All right?
I want to be a lawyer.
But it actually will help you remember it. All right? It actually.
Those are the only two.
Well, okay, so here it is.
Oh.
So if I have basically BE or B, right? Those can have less than 8. So boron and below can have less than 8 electrons.
So like,
Is that these?
Boron and below, boron, beryllium, lithium, yep. Boron, I should probably put Li. Lithium. What? What did I say?
I thought you said lithium.
Bolithium,
I was
yes.
like,
Bolithium.
That's one of them.
Carbon to silicon. From carbon to silicon, these will always have 8. Carbon to silicon will always have 8. But P in past could have greater than 8. All right, so P in past could have greater than 8. So boron and below could have a less than octet. Carbon to silicon will always have a full octet. But above phosphorus, you can have expanded octets, is what it comes down to. Okay?
That's so odd.
If that just is what it is, though.
Is there a reasoning behind it, or is it just?
Because that's how molecules bond. As we started reacting things, we thought, oh shoot, sulfur can have more. What?
were there like other valence shells for that, or was the electrons work?
Yeah.
You're just adding more. There's not really more valence shells. They're just more bonding sites. All right. So you'll see we can actually go up to 6 bonding sites when we get to tomorrow.
Is
It's
the
too
bond
All right.
site.
There can actually be a total of 6 bonding sites.
No.
So basically, it's like
I'm gonna
ideally
call.
you use
I'm
the
gonna call
octet
this.
rule.
Ideally, you'd use the octet rule, but you don't have to.
Octet rule then.
Yeah.
C to
Dude, we found
SI.
it.
So the octet rule's good for 8 elements. Okay?
Caleb.
Oh, that's
Ideally. But the good thing is, it's from C to SI, those are usually the ones in the middle. All right? So just whether the thing that is in the middle that matters. Let's keep going. I got one more thing I want to show you. How much time do I have left? I can show you this in 4 minutes.
Yes, it's a bug, dude. It has to be.
So
It's just like.
let's do NO3. Let's do NO3 minus a Lewis structure for that.
Oh no.
So how many
See, I felt okay, but that's simple.
how many valence electrons does nitrogen have?
Sin.
5. Take the
5.
average.
How many does oxygen have?
6.
6. So I've got 18. And a negative means I
Take one.
gained 1. So 5, 18 plus 1. So a total of how many electrons here?
24.
24 electrons.
Yeah.
Let's show 24 electrons. So I have nitrogen. Here's a nitrogen. Oxygen, oxygen, oxygen. Do you guys see what I'm going to have to do here?
Sort of.
No, actually, no.
Okay.
You're gonna have to,
So you gotta add
1,
lone
2,
pairs.
3,
you're gonna
4,
add 1
5,
to the
6.
end.
You have to double.
Be careful here.
Nitrogen is
Just do 2 of your oxygens. So I've got, so far, I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Right?
Yes.
If I draw 6 electrons here, is nitrogen going to be happy? There's going to have to be a double bond, right? There's going to be a double bond, so then it's going to look like this. And when it has a charge, I like to put it in a bracket with a -1. So if it has a charge, I like to put it in a bracket. Here's the thing. That works, yes?
Yeah.
But without drawing the lone pairs on the oxygens, would this work? Could I put the double bond here? Would that work?
In theory, yeah.
Okay, could I put the double bond also here?
Yeah.
Would that work? All 3 of those would work. Agreed?
Yeah.
This is called resonance.
Is there
Resonance.
circumstances all three doesn't?
They all of those could work, right? And resonance is more than one possible Lewis structure. More than one possible Lewis structure. More than one possible Lewis structure is resonance. So, the way you will see this drawn sometimes is like this. Nitrogen with a, kind of like this. Solid, dot, and your oxygens are like this. So the dots are showing, all right? All the dots are showing is that this bond can change. That double bond can go on any one of those oxygens. It has to go on one of them, but it's actually changing. And guess what? In the molecule, it actually is changing, all right? It's actually kind of moving in between, all right? It's kind of moving in between. Anybody know what this molecule is? Oh, wow, that was bad.
Oil well.
I cannot draw a hexagon.
That is a pentagon.
Pentagon.
Oh, what's it called?
Pentagon has 6 sides.
1, 2, 3, 4, 5. There it is. I'm trying to draw a hexagon. All right? This, you probably learned in biology.
Glucose.
If I draw these lines like this, all right? This is benzene, all right? Guess what? These double bonds move. They can be here, here, or here, or here, here, or here. And sometimes you'll see benzene drawn like this, 2, 3, 4, 5, 6, just with a circle in the middle. And the reason there's this circle in the middle is because those double bonds are just moving. It's resonance. We continue from here tomorrow. Continue from here tomorrow. This actually is not that hard.
This just felt like
We haven't got to write stuff
like
yet.
some forbidden knowledge.
Nice work today.
Caleb, this is an information hazard.